Hello, everyone, and welcome back to the AAS YouTube channel. And this one is going down the AAS Author Journal Series. And I am super happy to have Brian Thorsbro with us today. Hey, Brian.
Hello, everybody, and thank you for having me. I'm super excited to be here.
Well, I think it's a really lovely paper, and so I'm glad we're going to get a chance to go through it. And that is an awesome monumental bookshelf behind you.
It's a fantastic library. It's the historical library of the observatory here at Lund University.
Ah, okay.
We have plenty of monumental books as well. I think just behind me is the third edition of Newton's Principia.
Oh my goodness.
From 1726. Next to it, the French translation, just a few decades after. Wow. Down here, we have John Wilkinson's book on life on the moon from 1684 even. So pretty old books around here.
Yeah.
It's a fantastic place to sit in and be inspired by when you work.
That is totally awesome.
Love it here.
So I think you are our first one from Sweden, so that's fantastic. So.
And historical clock also.
And at even to the right time. Yes, awesome.
Yeah.
So Brian, what do you like to do for research besides reading French editions of the Principia?
I wish I was better at French, but yes. I'm a stellar spectroscopist, and I work with all things spectroscopy. I really like that part of the astronomy. Mostly because, I mean, looking at stars is fantastic, but looking at atomic physics is also really, really fun. And combining these two is kind of a sweet spot for me to be in. So I really like doing that.
Cool.
Yeah, and I'm a PhD student here at Lund's Observatory, depending in September. I started a bit late, even with all my gray hair.
So I started late as well, and I lost it all. But hey, it's all good. So how far along are you on your trajectory when you graduate?
So I'm graduating in September.
Oh, September! I missed that.
It's a funny time to graduate with all these things going on in the world at the moment. But
yes, it is. Yes,
cross fingers, it'll be fine.
Yeah, hopefully we all get this tackled over the next year or so, and all will be good. So, well, congratulations on being close to finishing.
Thank you,
Dr. Brian. And
cross
so,
fingers.
And so with that, why don't we go ahead and get into some stellar spectroscopy. So I'm going to share the article with people, and we are going to talk about detailed abundances in the galactic center, evidence for a metal-rich alpha-enhanced stellar population. And Brian, take us away.
Thank you. So this was really interesting work. So for the last couple of years, we have been working on doing abundance analysis of stars in the galactic center. And this, of course, is really, really interesting because you know, with abundances that connects into chemical evolution theories and so abundances for stars kind of gives a view into what kind of stars we have, in particular in an environment like the galactic center, which connects to evolution theories, for instance, galactic formation and evolution theory. All these evolution models, as we'll probably get back to down later in the article, predicts what kind of abundances you might find in stars if you follow a certain evolution track. And by doing these observation and measuring the actual abundances, we kind of get some kind of constraints or clues to what kind of evolution tracks could be possible. And in that way, we try to understand exactly what happened in this region of our galaxy. And galactic centers are galactic centers are also really interesting, especially because the nuclear star clusters are known to have empirical relation with their host galaxy. So that's kind of an indication that maybe these nuclear star clusters in the center of the galaxy have co-evolved with the galaxy itself. Nuclear star clusters are very, very dense and very, very bright, so we can see them far away in other galaxies. And that way, if we can somehow learn a lot about our own nuclear star cluster and assume that we are not too special, we can kind of use it to kind of understand other galaxies as well. So in a sense, that could be a much bigger stake in just finding out what our own nuclear star cluster is like, trying to investigate this. And this is what we think is really exciting. So we have been trying really hard at that. There are a lot of challenges trying to observe stars in the galactic center. First of all, it's very far away, so we need very bright stars. Second of all, there's a lot of dust between us, the spiral arms. And that means that we have to switch to more infrared wavelength regimes in order to penetrate through all this dust. So many of our challenges have been actually to get the photons in to our telescope and our spectrograph. And once we do that, we also have to actually develop spectroscopy for the infrared region. Spectroscopy in observational astronomy has been used for many, many years, but it's traditional, very restricted to the optical regime. So the infrared regimes haven't really been that much developed. So lately, I don't know if people probably heard about the Apogee survey. So the Apogee survey works around 1.5 microns in the wavelength range. And they have developed a lot of interesting science around that area. But in this work, we are moving out to the 2 micron range, which is outside what Apogee have developed. So we had to develop a lot of the spectroscopy and do atomic data measurements and stuff for that to get that working outside there. So there's been many, many interesting steps on the way before we actually could do this article this year. So the whole backstory is also really interesting. So if we look at what stars we have looked at, we can go down to figure 1.
Okay. Excuse me, everyone. Figure 1, and there we go.
There we have it.
Blow that up a little bit.
So here we can see a view of the galactic center as it's an image from the Galactic Nucleus survey. And the blue line is the 3.5 parsec projected distance from the supermassive black hole. And as you can see, we have a lot of stars, not in the exact center, because the exact center is way too crowded for observations. So we have been lying around, circling around the center and trying to find suitable targets to observe. We have been using the Keck telescope on Mauna Kea with the near-spec spectrograph. Keck does have adaptive optics, so we could have gone further in, but that will cost in the photons you get, and meaning you have to expose for longer time. So it becomes a balance of how many stars versus how close do you want to go to the galactic center. So we have really working, and we have had 3 observation runs, and we have 20 stars. So as you can imagine, it's a slow process. Each star about 45-ish minutes exposure time.
Okay.
And the galactic center is mostly visible on the southern hemisphere, but as you know, Hawaii is a bit up on the northern hemisphere. So there are only 2 periods during the year where we really can watch the galactic center, and then only on part of the night. So we get what we call half nights and share it with other. Okay. And as spectroscopists, you don't get the dark nights, you get the bright nights, because the spectrograph is not that sensitive to light pollution as other things. So there's a whole bunch of things going into this.
Absolutely.
Also part of the fun of the work. So these are M giants. Another thing with M giants is that they're very cold. We need these M giants because they're also very bright, but they're also very cold. That means that there's a lot of molecules in it, which again means that if you look at the spectra of an M giant in the optical wavelength regime, you will find the optical part of the wavelength regime is completely littered with molecular lines from titanium monoxide, which means that actually M giants in themselves have not been classified and observed that much. So after struggling a bit with our first targets, we decided in one of the upcoming runs to include M giants from the solar neighborhood regions, solar neighborhood Milky Way disk stars.
Okay.
So we have 20 stars from the galactic center, and we have 7 stars from the Milky Way disk. And this actually enables us to do a differential study between those two sets. So in a sense, I mean, we can't be worried that you will have systemic problems when you do go into this M giant and the 2-micron infrared wavelength bands. There could be things that are different than doing other wavelength rings on other stars.
Right.
That could make systemic differences. So if we get some abundances in our with our measurements, how can we be sure that they are comparable to other measurements done for other stars? So that's why we also went for having a control group, so to speak. And if we if you take figure 2, as we see here, we can see that we have tried to cover as broad a range as possible with our sample to make sure that we are not too much biased by our observations. And if we go down to figure 3.
I got one question on figure 2. What is that black arrow pointing to?
That's the reddening arrow.
Gotcha. Thank you.
Yes, you're welcome.
I understand. Yep.
Yeah, you should have written that.
That's okay.
If you go down to figure 3, so you can see this is part of the analysis of this M giant spectra I've been talking about. And there's a lot of molecular lines. Particularly, we have CN lines all over the place. So it's very, very important that we actually get to find these lines and model them well. But of course, we can't be guaranteed to model them extremely well. So we also try to make sure that those lines we actually use are as free of this CN molecule as possible. So what we have been doing.
What's the resolution here? What's like delta lambda over lambda?
So for this plot here, I think it's about 100,000.
Okay.
This is just the modeling to kind of convince ourselves. So here we're trying to convince ourselves that if we use this iron line and this silicon line for abundances, we are not hurt by not being able to do the CN modeling completely and properly.
Gotcha.
If we don't have a super correct carbon or nitrogen abundance, it will not affect our silicon abundance determinant too much. I mean, when the C and N and O abundances are all connected in CN and CO and OH, and you need to do chemical equilibrium and stuff for your atmosphere models. So these, if you become depending on doing that too much, you are asking for trouble. So we're trying to find these atomic lines that are free of these blends, so to speak.
Right.
So we have done that analysis and tried to convince ourselves that the lines we're using, which we see in table 2, I'm not going to go into all the lines in details, but these are the lines we have found to be the least blended of all of these two species. And then we get to work. We run our stellar models, Marx models, a classic used in spectroscopy these days, from Uppsala here in Sweden. So we can run them ourselves. We can make our own Marx model. Cool. And we then do different grids of stellar spectra and go through them. Some of the important parts of the doing these models is, of course, that we get the stellar parameters right. And one of the most important stellar parameters are, of course, the temperature. We also have the surface gravity and the microturbulence. I'll come back to the microturbulence, but if you look at the temperatures, we use some empirical relations originating back from Bloom 2003 and have been improved over time, where you look at the CO band heads of the molecules, and it appears that there are a empirical relation between the equivalent widths of these CO band heads and the temperature of the stars.
Okay.
And this has been used for quite a lot of stars for quite a long time, so it's fairly we trust it fairly much. But there's a lot of patchy reddening towards the galactic center, and of course you can be worried that maybe there is some dust in the way or something else that will affect your temperature determination. So we actually also use a second method that we developed 2 years ago, and that is that these cool M giants have some very strong scandium lines. And in 2018, we wrote a paper about that and how these strong scandium lines seems to be extremely temperature dependent. So we went to our seven M giants we took in the Milky Way disk and looked at the size of the scandium lines, and then we used the apogee temperatures from these stars. We also compared them to other temperature determination using Gaia stuff, but we found that we stuck to the apogee temperature, and using the equivalent width of these very strong scandium lines that are temperature sensitive and connecting to these apogee temperatures, we can make relations between the equivalent widths of scandium and temperature in principle, like the same way that you do with the CO2 as carbon monoxide molecule band heads. And then we translated that into the galactic center stars to see what kind of temperature we will get out using that method. And as you can see in table 3, they are not that far off each other. There's one star where we didn't have the CO bandhead temperature. But apart from that, these temperatures are fairly close to each other. So in the end, we said, okay, let's take an average of this, and this became our temperature of the stars.
Does one worry about non-LTE stuff?
So, so for the scandium, you worry a lot about LTE and non-LTE, and that's a serious concern because if you look at that's actually something we investigate quite a lot in our 2018 paper. The biggest reason for these lines to be so big, though, are that we have a very, very strong hyperfine structure in scandium.
Okay.
So the onset of saturation is pushed back. So actually you can get, we have, in that sense, compared to the hyperfine structure, we have low resolution in our spectrum. That's why we see it as one line. But actually it's many smaller lines next to each other. And in a sense, when they convolve together, they become one big line that actually goes deeper than you would have expected if there's been just one line and it is saturated.
Yeah.
But even taking that into consideration, for the colder stars, we still have problems doing the abundance analysis, and that must clearly be because of non-local thermodynamic equilibrium conditions.
Okay.
So we are afraid of doing exact scandium abundance determination because of that. But when it comes to the temperature sensitivity, I mean, scandium is a minority species in 3,000 to 4,000 K range. So we think we can still use it for that because small temperature changes will have large impact on the line itself.
Okay, thanks.
So yeah, that's also a very interesting paper from 2 years ago. Also in APA.
Check that one out.
With it plugged in for that. But if we move along, so now we have the temperatures and we want to find the metallicities. And we are looking at these M giants, and they are old, all of them. So actually, one thing we use for our benefit is that the isochrones of these old stars overlap, basically for all the ages we think these stars can have. That means that we don't really have For M giants, we are so far up the tip that the isochrone of age 3 to 10 gigayears is kind of lying on top of each other, meaning that we don't really care about that degeneracy. Actually, we use it to our advantage and say, okay, that means we don't have to worry about age. So now we can just worry about temperature, gravity, surface gravity, and metallicity.
Okay.
So actually, when we do our grid of metallicities and search through what models we can get to fit best, we say, okay, at this metallicity with that temperature, and we plug in the surface gravity that the isochrone says that we could expect to find. So in our 2017 paper, we tested this method against all kinds of apogee stars and found a good match. So we are still using that method today, and we use that to make sure that our log Gs are consistent with the other stellar parameters that we're using. Is that clear?
Yes. I'm good. Yep, I'm good.
Good. And so in that sense, we get to lock down the stellar parameters of the star, and we use this to then do a metallicity distribution functions, as we can see in figure 4. So in 2017, we examined 17 of the stars for metallicity distribution function, but since then we have done a lot of work on refining stuff, so we thought to do it again. And you can see the black ones was from the old analysis and the red one is from the new, and not that much change. So in a sense, that's a good news. But we will consider the red more accurate than the black. One notable change is that the highest metallicity star moved down a little from 0.64 to 0.50. Okay. This is interesting when we look at other metallicity distribution functions that's been done in the nuclear star cluster. There has been done some lately by Du et al. And Feldmaik-Haus et al., where you have also very metal-rich population going all the way up to 1 dex.
Okay.
So we are not getting all that way up like they are. But they have lower resolution, so yeah. It's something to discuss which way they're going.
Right.
That gives us all a job to do, I guess.
Definitely.
So, but with all these with these stellar parameters in place, we move on to try to figure out if we can do some of the alpha elements of the nuclear star cluster, because that's an essential part of chemical evolution. How is alpha rich, alpha poor? We all heard about the dichotomy between the thick and the thin disk out here in the Milky Way, where the thick disk is alpha rich compared to the thin disk and stuff like that. So it's it's a central part of chemical evolution theories to figure out the amount of alpha elements, because of supernova type 2 versus supernova type 1a enrichment into the medium.
Yes.
So we went into we have several lines from several alpha elements present in our spectra, but the only one we were really confident using was the silicon one. Some of the others were very either CN blended or very strong and moving into an NLT issues.
Right.
Okay. So with silicon, we had fairly weak lines, as you would call them, and we tried to investigate those in detail. We also actually did some NLT departure coefficient calculations for silicon, but they showed that departure coefficients were not very strong, so we didn't have to worry too much about that. Mm-hmm. So here's what when it becomes interesting. So when we look at these silicon abundances, as we can see in figure 5, we have the blue disks are the Milky Way disk star, and the red triangles and squares are the galactic center stars. Triangles means that we are fairly confident they are actually inside the nuclear star cluster. Squares means that we think they're probably further out and belonging to the nuclear stellar disk.
Okay.
And that's also an interesting thought. I mean, there's a lot of uncertainties in exactly placing the stars, because also these two populations are mixed in different places and stuff like that. And all these dynamical models you need to have in place to determine where they belong. But with that in mind, it's if some of them belong to the nuclear stellar disk and some of them belong to the nuclear star cluster, but they're still showing abundance like same trend, that will also be interesting to take into account, that maybe these two stellar population groups have somewhat of the same evolution model maybe.
Could one use kinematics to help distinguish those?
So better models for the gravitational potential could be used. I don't think they include actually the supermassive black holes in those models when they do these orbit analysis. Better reddening maps. Some of them, two of these stars might actually be a bit behind the nuclear star cluster, depending on how reddened they are and stuff like that. So better reddening maps, better models of the gravitational potential, I think could be used to improve that. But I think they are pretty good already. It's clear that those three squares are probably not members of the nuclear star cluster.
Okay.
But there are caveats. I mean, we cannot be completely sure. But what's interesting is that for the left stellar population group, they're kind of the same alpha abundances. But for the right, for the metal-rich part, there seems to be a difference. I have to say it's a small number statistics, so but still, when you plot it like this, it looks like there could be a difference, right?
Right.
And this is, of course, really, really interesting if this is the case. I mean, the primary interest is actually that it shows that environments in the Milky Way disk out here is different from the environment in the galactic center. This is perhaps not a big surprise, but it's actually something we need to know whether it is the case or not. And this could actually be an indication that there could be reason to think that the galactic center environment is different in ways we need to understand better than the environment we have out here. And there's a lot of reasons this could be interesting, not only because when we do these big surveys, we do a lot of machine learning, and the machine learning is very, very good at finding signals that we are expecting to find. So if there is a different signal to look for, we need to make sure it's part of the training sets. So there is an argument for why we should have a very detailed manual analysis going on here of these stars in the galactic center, with a proper understanding of also the atomic physics and stuff and everything. Cool. So in that sense, I think it's really, really interesting that we're finding this, and it's something we really want to explore further. We have compared it to other studies. If we go on to the next figure, let's see where we can find it. Oh yeah, let's take figure 6 first on the way. Of course, when we find this, we ask ourselves, is it real?
Yes.
So here we have taken the raw observed spectra, and this is a resolution about 23,000.
Okay.
And pulled it out. This is no analysis or anything. This is just the raw spectra as we get it out of the data reduction. And the blue ones are the three Milky Way disks that are metal-rich, and the red ones are the galactic center metal-rich stars.
Yes.
And we try to make sure that the continuum is the same for both sets, and then we look at how deep does the iron line differs compared to the silicon lines. And we do think that the silicon lines are stronger than the Milky Way disk in a way that the iron lines are not. So that kind of seems to suggest that maybe we're not completely off track with our abundance analysis.
Okay. Yeah.
Yeah. This is just looking at the raw output. There is a lot of, you can discuss a lot what the CN impacts and stuff like that. But that is also why we modeled these two lines to check sure,
Earlier figure, yeah.
to make sure that we didn't have a CN line fooling us in the silicon line. Of course, I have to say that it could be that our CN line is not line list is not complete, so there's definitely also that possibility.
Yeah.
But let's yeah. But this when it's not the only silicon line we're using, so also we have that.
That's good.
So if we go down to the next figure, where we compare these results to, this is then bulge studies.
Okay.
Figure 8.
Figure 8.
And here we are comparing our stars, M giants. So again, we have the blue circles, blue disks, like before the Milky Way disks, and then we had the red, the galactic cinder stars, and overplotted some micro-lens bulge dwarfs in black, and some K giants also from the bulge.
Okay.
So in a sense, the overall trend by going down and flattening out seems to be kind of the same, at least the blue Milky Way disks.
Right.
Seems to agree. There's a bit of a scatter in the bulge giants. Again, we think that the silicon signal for the metal-rich galactic cinder stars is a bit off compared to the others. It's nice to see that the blue disk stars are in somewhat agreement with what the other are finding, even which should hopefully be the case. Then we looked into what does this then mean? How can this be interpreted? Some chemical enrichment scenarios. I could say these figure 7 is just a continuation on the orbit analysis. But if we go down to figure 9 and 10.
Okay, I'm with you.
Sorry.
Okay, so we have some chemical evolution lines.
Yes, so here we are going into the chemical evolution lines, and there are a lot of parameters to tweak on a chemical evolution plot, but they're still important because they kind of, these simple model kind of gives us an idea on how things could look. So in a sense, it's kind of exploring what kind of chemical evolution models would be able to explain an outlook like this. And the left one is where we have a normal star formation happening, and then at some point there's a second infall of gas, as they call it, of pristine gas that dilutes the metallicities that has been built up in the existing gas, and it also increases density, and then starts a second star formation period.
So the evolution here is you start to the left, you go down, you show your normal thing, then you're going to dump in some gas, and so this is what generates the loop. So then you go back and you loop back and come back. Is that right?
Yes.
Okay.
So it's a kind of like a timeline you follow down on this along this evolution track.
Okay.
There will not be stars everywhere on the line because there will be periods with low density and stuff. So we don't expect to find uniformly stars all across the track. So in that sense, it's okay that there are parts of the track that doesn't match any stars.
Like a Hertzsprung gap. All right, they're just fast phases, perhaps fast phases of evolution, and you just don't see any.
Yeah, exactly. Probably we just need to observe them. And if you look at this model on the left is just there's a second infall coming from somewhere. Where that is coming from is of course a good question.
Could it be cloud?
It could be. I mean, it could be a lot of things. It could be maybe it could be an accretion event of some dwarf galaxy that carries some gas with it, or something like that.
Yep.
And then on the right side, we imagine that what if we had a stop in star formation? Maybe there's a buckling of the disk or something else that suppresses star formation for a while, and then it restarts. And what will that look like? And the stop at different times, and that of course is also able to reproduce our result. So there are multiple models that you can kind of go in and investigate here. And I mean, this is really interesting. Also, we are talking a lot with some of our colleagues who are doing simulations, and they also want to, when they simulate all these galaxy evolution, they also end up with some kind of chemical distribution they want to compare to results like this. So this is really where we are heading at the moment, trying to figure out, I mean, what can it be that there is a little extra silicon in the galactic center?
Right. So that the concern is that if you just ran a simple chemical evolution model, that you would not pick up both groups.
Yeah.
Right. And so you're going beyond a simpler chemical evolution model to try and induce some shapes, shall we say, in the silicon to iron plot in order to pick up both groups. Yeah.
Yeah.
Okay, I'm with you.
Yeah, I mean, these models are these models are, I wouldn't call them simple, but I mean they're kind of not too complex, so you can actually explore different scenarios, which is really nice. That makes them really useful.
Yep.
So this is kind of where we are at the moment.
Okay.
Of course, we will really like to have more observations, and we will also like to have them in higher resolution. And particularly, I mean, we're fortunate that the near spec on KEGG has been upgraded, or has just been upgraded to 30-something resolution, 30-something thousand resolution.
Cool.
We also have the CRIRIS Plus spectrograph coming online on VLC, just around the corner, waiting for it to go into commission at the moment. And there are a lot of other spectrographs as well, like the ICRINS, that's going on Gemini South.
Nice.
And we hope to get a little leg in there as well. We're currently in what they call third queue, so if the weather is good, we'll get some observations. Okay. So we want to expand this further, and we think there is a real need for doing high resolution manual spectroscopy. I mean, we think it's we love machine learning, but there has to be someone that
guides it.
That guides it in front, and there has to be someone that do this manual, gritty, high detailed work, and say, look, here's a signal that's interesting. We need to have this when we look for signals and stuff.
So when these new as these new facilities come online, is the hope or the anticipation that you could perhaps double, triple, factor of 10 the number of stars that you're doing by hand? So I think you had 20 in this one, so maybe get 40, get 100.
That will be amazing, especially with the new facilities, the large telescopes. When they come online, we can do much more stars in shorter time.
Okay. I hope, yes.
And we even thought about if we could, so we don't think we can do the Andromeda Galaxy nuclear star cluster there, but maybe you could do some integrated light spectroscopy and compare it. But if you, at some point, if you can move outside the Milky Way also, that would also be super interesting. And we hope there's also an avenue down that road in the future, maybe some more. I mean, that's also part of doing the nuclear star cluster, is that we have so much light from other nuclear star clusters.
Yeah, cool. All right, so the future's
bright.
Right. Gotta wear shades. Okay, that was a nerdy joke.
Yes, that's what we do, right?
What we do. All righty, awesome. Brian, I want to thank you so much for spending a little time with us today and walking through your really lovely paper.
Thank you very much for having me. I really enjoyed it.
All righty. Thank you, everyone, and we'll see you on the next one.
Bye-bye.